Now, we've got a number of simplified cases. I've got the electric field of a rod on a point that bisects that rod. I've got the electric field of a ring on the axis of that ring. I have the electric field of a disk on the axis of that disk, and I have the electric field of a plane on a point that bisects that plane, that is perpendicular to that plane. Sorry, if it's plane, obviously any point where a perpendicular hits it will seem like the middle. Now, the next learning objective in the A level is to learn how to use several of these together. For example, suppose that I've got a rod. Suppose I've got two rods. Each one of these, let's call this 2 meters, 3 meters, negative 2 meters, negative 3 meters. I've got two rods, each 1 meter long, and each with a net charge of 1 microcoulomb. Now, I want to know what the electric field is here at point P. Just looking at this, this looks like there might be a problem because I only have this special case for an electric field if I'm on the center of that line. And I don't have that. Is there a way to do that? Yes. Here's what I'm going to say the sneaky way out is. Suppose that I envision, let's see, 3 meters, negative 3 meters. One rod that goes from x equal to negative 3 meters to x equal to positive 3 meters, and that has a line charge density of, well, 1 microcoulomb per meter will work for this section and for this section, but not for the middle. So suppose I have a line charge density of 1 microcoulomb per meter for that case. Now, that would work, but I'm getting too much. I'm getting this stuff in the middle. So the sneaky bit is to envision a second rod that goes from y is equal to 2 meters to y is equal to negative 2 meters, and say that that has a line charge density of negative 1 microcoulombs per meter, because in that case, between these two differences, between x is equal to y is equal to negative 2 meters and y is equal to positive 2 meters, the net charge in this region will be 0. A line charge density of negative 1 microcoulombs per meter plus a line charge density of positive 1 microcoulombs per meter. So I'm going to make the argument that these two setups are the same. And starting from there, starting from that realization that yes, there is a way to sneaky my way out of this, we do okay. Because I look at that then, and I've got that okay, the electric field here will be positive charge radially outward in x. Now, that'll be due to this, well, the imaginary whole line of positive charge, which will be K, okay, the entire charge here would be 6 meters long times 1 microcoulomb per meter, so I'd have K times 6 microcoulombs divided by R times the square root of R squared plus L over 2 squared minus or I should say, plus the electric field due to this imaginary second wire or second rod that only exists to cancel out the effect from the first rod, or in this case it would be K times -4 microcoulombs over R times the square root of R squared plus L over 2 squared. And that sum, of those two cases will give me the correct number. I didn't put numbers in here except where I wanted to make it clear about the total charge on the imaginary whole rod and the imaginary negative rod that cancels out the middle. It cancels out and creates that gap because, hey, the temptation is toss numbers in, but toss numbers in only at the very, very last step when you're absolutely done. The A-level questions will follow this pattern.